Hi everyone, welcome to the video lecture series of Theory of Automata and Formal Languages. We are into unit number 2 where we are learning about regular expression and its various topics. In my previous lecture we have understood how to convert a particular finite automata into a regular expression by using the state elimination method, and we have discussed 5 examples on it, and we have seen few cases as well. Okay, and suppose if you are not okay with that particular method, you can also use this method. If suppose in university question paper, suppose anyone is attempting and you got a question that solve this finite automata and convert this into regular expression simply, then you can use either of the methodology, and if they urge you or if they ask you that you have to convert by using this particular method like Arden'S theorem or state elimination, then you have to follow it. That's why I'm teaching both the methodologies. Okay, Arden'S theorem is itself an important topic and is actually a very frequent type of questions being asked in university question papers and all. Okay, and if you're attempting any kind of competitive exams as well, by using this Arden'S theorem, it becomes a little bit of short. Okay, or else you can also go with the elimination method as well. That depends on what kind of methodology you are accepting. Okay, so let us start off with this session where we'll be learning about the conversion of a finite automata to regular expression by using Arden'S theorem. Okay, so I've taken an example, but before going into the example, there are certain steps to be followed. Okay, and to be honest, I won't be describing these steps right now. I'll be directly jumping off with the example and I will let you know how to work it out. Okay, so fast as we can do, we can start off with the steps. Okay, let us take the example. The example is given to you and we'll be trying to solve this example by using the Arden'S theorem. So how to do it? So first of all, you have to check that you have to write down the equations for each state and check some incoming edges. Okay, how to do that? Okay, now we are having how many states? We are having 4 states we are having, right? Now for every 4 states we have to make 4 different type of equations. So how to do that? See, for every state there is an incoming edge, right? Based on incoming edge only you have to write down the equations. Okay, for that you have to check it out with the first example. So you can write it down, that write the equations for each states present over here. Okay, so besides writing that, I will directly jump off to the equations. The first state is what? Always start with the initial state. Initial state is Q1. So Q1 will be having one expression. Okay, first always remember that Q1 is always having this, being Q1 as the initial state, it will always have an incoming edge which is empty. See, this is an incoming edge, right? So this is always an initial state symbolic representation, but it also have an initial null empty transition, you can say. So that means Q1 always have epsilon as the initial transition, correct? Apart from that, how many transitions are there? Incoming edges. This is an incoming edge and this is an incoming edge. Apart from that, no more. Okay, so how to write down this for B? It is coming from Q2, so I can write down Q2B. State and what transition it is coming, that we have to write it down. Similarly, I have come across with Q3, so Q3, what is the transition it is coming? A. This is equation number 1. Is this clear? I think it is clear to everyone. See, Q1, I will start off with the initial state being Q1. So what is the initial incoming edge? This is epsilon is the initial incoming edge, correct? This is, then we are having B which is coming from Q2, so I have to write down as Q2B. Again A is coming from Q3, so I have to write down Q3A. So I am done with Q1. Now I will move to Q2. Only with the case of initial you will be having epsilon. Apart from that, no more. Okay, and that is the reason why we are using Arden'S theorem. I will let you know. Okay, now Q2 will be having any incoming edge? Yes, we are having one incoming edge I am having, correct? So this will be your Q1A. So this will be equation number 2. Then we'll move to Q3. Q3 I am having an incoming edge that is from Q1. So it will be Q1B. So this will be equation number 3. Now Q4. Q4 is having 1, 2, 3, 4 incoming edges. If you check, A comma B means A and B 2 different transitions, correct? So that means it will be, first it will start off with Q2A, then it will start off with Q3, B, then it will start off with Q4A plus Q4B. So this is equation number 4. Okay, now how to proceed forward, which equation I have to give importance, that you should know it. See, if I look into the transition steps, it is mentioned that transition diagram should not have any epsilon transitions. Okay, if you are having any epsilon transition, then you have to convert it into NFA, but that will not be given to you. Don't worry about it. Okay, but you will never know what can come. Okay, so in step number 2, it says that suppose vertices are q1, q2, q1 and qy is the final state, then we'll be having an edges and we have to label those edges. This is what the labeling is all about. And after that, what we have to do, I will let you know. See, when a particular set of string is accepted, when it reaches the final state, correct? That means the equation that I have to give much more importance is the final state. So I have to stick on to the final state only, and apart from that, other equations will just be an helpful one. Okay, so how to do that? So let me check it out. So basically, I'll be starting off with Q1, equation number 1. Equation number 1 is, say, just you have to use the concept of substitution method. So Q2, can I convert in Q1? Yes, I can convert in Q1. So I can write down that in place of Q2, I can write down as Q1 A, and already B was there, so B will be S1. And in place of Q3 also I can convert it into Q1, correct? So that means I can write down as Q1B, already it was A. How I did it, since Q2 is equals to Q1A, this is just a substitution method, Q3 is equals to Q1B. Correct? So you have to mention this, or you can write down from equation 2 and 3. Okay, now if I write down like this, epsilon plus Q1, if I take a common, then it will be AB plus BA. Okay, now you can check it out. Sometimes you'll be getting 4 equations, you'll be getting 5 equations, you'll be getting 6 equations, but it's not mandatory that every equation you have to use it. Okay, just you need to focus in the final state equation. Final state equation is which one? Q1 is the final state, correct? So I have to concentrate only on Q1. Now I'll be coming across one particular point, what Arden'S theorem states. Arden'S theorem states that if we are having an equation of the form R is equals to Q plus RP, then it has a unique solution, R is equals to QP star. Arden'S theorem states like this. Now if we look into this equation, okay, just give me 1 minute. Okay, if you look into this equation, this Q1 is acting like R, okay, this epsilon is acting like a Q, this Q1 is acting like a R, correct? Q1 and Q1 should be always equal, sorry, the R and R should be always equal, that is equal, and this part is acting like a P. Clear? So this is of which format? R is equals to Q plus RP. Now you have to use your logic. Definitely this by using Arden'S theorem, what will be the answer? You have having a unique solution for it, right? So according to Arden'S theorem, R is equals to QP star. So what is R over here? R is nothing but your Q1, correct? Q is what? Q is epsilon. P means what? AB plus BA whole to the power star. And what we need finally? We need the final expression, right? And we got it. And if you solve this, then the answer will be AB plus BA whole to the power star. Therefore, the final regular expression will be what? AB plus BA whole to the power star. Now, if you have used, suppose, state elimination method, so many way of working it will be. Like it will be of n number of states, right? You're having 1, 2, 3, 4. You have to eliminate first this element, then you have to eliminate this one, then you have to eliminate this one, and finally you'll be getting one transition. So it will be a very, very hectic for you. And if you have used this Arden'S theorem, see how easy it is, and now we got the expression. And if you use Arden'S theorem, this will definitely give you the perfect expression. Okay, there is no doubt about it. I think everyone is clear about the Arden'S theorem example. And if you're having any doubt or any comment, please give me a suggestion in the comment box, or any query you can comment down in the comment box. Okay, so we'll be moving into one more example and we will check it out how to work on that as well. Okay, let me check. Okay, so we'll be taking one more example, or 1 or 2 more example, and we will try to solve by using the Arden'S theorem, and that we'll be discussing in the next video. and where I will try to give you a different variation of an example, and you also try to work with that particular diagram by using state elimination method, and you can compare the efficiency, or you can compare the time, how much it is taking. Okay, in that way you can understand. Okay, so we'll be meeting you in the next video, where we'll be learning about one more example by using Arden's theorem. Thank you for watching.